Introduction to Statistics, Chapter 9, Estimating the Value of a Parameter, Section 9.1, Estimating a Population Proportion. A point estimate is the value of a statistic that estimates the value of a parameter. If you recall from Chapter 1, a statistic is a measurement from a sample. A parameter is a measurement from a population. When a sample is drawn from a population, the point estimate for the population proportion is p hat, which is equal to x divided by n, where x is the number of individuals in the sample with a specific characteristic, and n is the sample size. A confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. The level of confidence represents the expected proportion of the intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted by 1 minus alpha times 100%, where alpha is the area under the normal curve outside the interval. For example, if alpha is equal to 0.05 or 5%, then the level of confidence is going to be 0.95 or 95%. If alpha is 0.01 or 1%, then the level of confidence is 0.99 or 99%. Now let's go the other way. If the level of confidence is 90% or 0.90, then alpha is 10% or 0.10. Also, if the level of confidence is 85% or 0.85, then alpha is 15% or 0.15. Now, interpreting the meaning of a 90% level of confidence. Many times this is misinterpreted. And the incorrect interpretation is, once you have an interval, don't say there is a 90% probability the parameter lies within the interval. That is incorrect interpretation. The correct interpretation is, if you constructed 100 different confidence intervals, each based on a different sample from the same population, then we will expect 90 of the intervals to include the parameter and 10 not to include the parameter. Okay, confidence level deals with doing several different intervals. And now those intervals, 90% of the intervals will contain the population parameter. Okay, the margin of error E in a 1 minus alpha times 100% confidence interval for a population proportion is given by E is equal to Z sub alpha divided by 2 times the square root of p hat times 1 minus p hat divided by n, where Z sub alpha divided by 2 is known as the critical value for the confidence interval, p hat is the point estimate for the population proportion, and n is the sample size. Finding a critical value Z of alpha divided by 2 for a given level of confidence. Well, option 1, the most used levels of confidence and their critical values are listed at the bottom of Table 5, standard normal distribution of your formula sheet. So if you would look at your formula sheet, which you'll be given in the exam testing center when you take your exam, and you should be able to print it off at home and use it. At the very bottom, on the left side, you will see this table. It says confidence interval critical value, Z of alpha divided by 2. You have the level of confidence on the left. So they do 90%, 95%, 98%, 99%. And they give you the critical values. 1.645, 1.96, 2.33, 2.575. So this table gives you the critical values for the most used levels of confidence. Let's say you didn't have one of those levels of confidence. Then option 2, using StatCrunch and a normal calculator. Leave the mean 0, the standard deviation 1. Recall that Z of alpha divided by 2 is the Z value such that the area to the right of Z is alpha divided by 2. You choose greater than or equal, enter alpha divided by 2 in the answer section, and click compute to find Z value. You learn to do this in Chapter 7. A confidence interval is usually listed in one of 3 methods, where p hat is the point estimate and E is the margin of error, based on a given level of confidence. Okay, the simple notation would be p hat plus or minus e. Now, an example of this would be like 0.45 plus or minus 0.125. Now, this notation doesn't make a whole lot of sense to a lot of people, so let's change it. You know, a proportion can be based in percent. So this would be the same thing as saying 45% plus or minus 12.5%. And that would make a little more sense to most people. But either way, it could be written as a decimal or as a percent. They both have the same meaning. And you will see this a lot of times around elections. You know, in elections, they will tell you that one candidate may have 48%, the other candidate may have 51% of the votes. Then they say plus or minus 3%. Well, that plus or minus 3% is your margin of error. Algebraic notation. You could say P is greater than P hat minus E, less than P hat plus E. This is trapping the population proportion between a lower limit and an upper limit. So, in this case, we'd have 0.45 minus 0.125 and 0.45 plus 0.125. Do the math. Now we get P is greater than 0.325, less than 0.575. Now we have an interval. Now, that's in decimal form. We can also look at this in percent form. This would mean that P is greater than 32.5%, less than 57.5%. Last, interval notation. This is where we just take an interval, P hat minus E, comma, P hat plus E. We just put the lower limit and the upper limit. So we'd have 0.45 minus 0.125, 0.45 plus 0.125. So you get 0.325, 0.575. You notice this is very similar to the algebraic notation, except for you're not using the inequalities. And we could also do percentage, 32.5%, 57.5%. Okay. Now, the P hat minus E is known as the lower bound. The P hat plus E is known as the upper bound. Recall conditions that must be met in order to estimate the population proportion using a sample. Remember from our earlier chapter, they were n times p hat times 1 minus p hat must be greater than or equal to 10, and n is less than or equal to 5% of the population. Finding a margin of error in confidence interval by hand when x, n, and the level of confidence is given. Well, here's an example. In a survey of 700 community college students, 481 indicated that they have read a book for personal enjoyment during the school year. Determine a 90% confidence interval for the proportion of community college students who have read a book for personal enjoyment during the school year. Well, first we have to pick information out of the problem. So in this case, n is 700. Okay, we're talking community college students. So 700 would definitely be less than or equal to 5% of all community college students. Okay, and then you could also do n times p hat times q, but we don't know p hat yet. We have to find p hat. So x is 481. So p hat now is x divided by n, 481 divided by 700. And if you round that off to 3 decimal places, you get 0.687. Next, level of confidence is 90%. Okay. Now, 90%, if you looked at that table, 90% was in the table, and alpha is 0.10. So z of alpha divided by 2 is z of 0.05. You could either go to the table or you could go to StatCrunch to find 1.645. Either way, you'll get the same answer. The table, I think, is going to be a lot quicker. Then we have the formula. E is z sub alpha divided by 2 times the square root of p hat times 1 minus p hat, all divided by n. So now we substitute numbers in. So we have the 1.645, we have the 0.687. You take 1 minus 0.687, you get 0.313 divided by 700. Use your calculator correctly, you should get the answer shown. And then round it off to 3 decimal places, 0.029. So the interval is going to be p hat minus e, p hat plus e. So remember, p hat was 0.687, e was 0.029. So we take 0.687 minus 0.029, and then we add it. And we get 0.658, 0.716. And this would be our interval. Hence, P is trapped between 65.8% and 71.6%. And that's the population proportion. Now, finding P hat and E when given a confidence interval. Let's say I was giving you a confidence interval. Okay? Recall what an interval P hat minus E, P hat plus E represents. This means that P hat is dead center. You're going to take P hat minus E, which moves you to the left. You're going to take P hat plus E, moves you to the right. The P hat minus E is the lower bound. P hat plus E is the upper bound. So where is P hat? P hat is dead center. Hence, P hat is the average of the lower and upper bounds. Or P hat equals lower bound plus upper bound divided by 2. Now, what about E? Well, E is half the distance from lower bound to upper bound, or E is upper bound minus lower bound divided by 2. If you look up here in the diagram, you know, this is P hat minus E, P hat plus E. So the distance from P hat down here is E, this distance is E. So if I take the distance from the upper to the lower and divide it by 2, I would get E. Now, using StatCrunch to find a confidence interval for estimating a population proportion. Now, I'll go through the steps here, and I'll show you what you get, and then I'll call up StatCrunch and actually go through it for the same problem we just did. All right. First, click the question help at the top right of the problem to open StatCrunch. Second, click Stat on the top menu. Highlight Proportion Stats this time. Highlight one sample. Click with summary if you're given X and N, or with data if you're given a list of data. Most of the time you're going to be given the X and the N, so it's going to be with summary. Third, enter the value for the number of successes, that's going to be X. Enter a value for the number of observations, that's going to be the sample size, N. Click circle beside confidence interval for P. There is a place there for a hypothesis test, which we will do in the next few chapters. But right now we're doing confidence interval. Okay, we're going to enter the level. This is the level of confidence as a decimal. And then you're going to leave method alone. Leave it standard walled. And finally, click compute. Now, same problem. Okay, so we'd have to go through the problem. If we're going to use StatCrunch, we need to know the sample size, N. We need to know the number of successes, which is X, 481. And we need to know the confidence level, which is 90%, but as a decimal, 0.90. These three things are needed if you're going to use StatCrunch. Now, when you open StatCrunch, you'll see a screen like this. You're going to put in the number of successes, in this case 481. The number of observations was 700. You're going to click the circle for confidence interval for P. You're going to put the level 0.90 in. You're going to leave standard walled alone. And then you're going to click compute. And when you do this, you will end up with this screen. Now, what does this screen tell you? Well, P hat would be the sample proportion. So right here would be P hat. Okay? The lower limit and upper limit are given. So the interval would be 0.658, 0.716. And if you recall, this is the same interval we got when we worked it by hand. But as you can see, StatCrunch would be a lot easier. And so that means P is between 65.8% and 71.6%. Now, let me end this a second, go over here to StatCrunch and go through what I just talked about. Okay, you would open StatCrunch. Once StatCrunch is open, you click Stat. You highlight proportion. You highlight one sample. In a later chapter, we're going to do two samples. Right now, we're doing one sample. And we have the X and the N, so it's with summary. So we click with summary. Number of successes for our problem, if you recall, was 481. The number of observations was 700. Now we click confidence interval because it's up here on hypothesis test, so we click confidence interval. The level of confidence was 90%, so I change this to 90%. I leave standard Wald alone for the method. I click compute, and here's the screen that I showed you in the PowerPoint. You get the sample proportion right here, 0.687, lower limit, upper limit, so you can make your interval. Okay, so this is you going through the steps using StatCrunch. Now, determine the sample size needed to estimate a population proportion within a specific margin of error. Okay, if a prior estimate p-hat is known, if somebody did a sample already and they have a p-hat, it's always wise to use their estimate because that'll cut down on your sample size when you do your estimate. So, the sample size required to estimate the population proportion P with a level of confidence within a specific margin of error E is given by N equals p-hat times 1 minus p-hat times the critical value divided by E quantity squared. And we always round N up to the next whole number. So even if N would come out even, let's say N came out to 356, round it up to 357. You always round up. If it was 356.25, round up to 357. It was 356.89, round up to 357. So you always round up to the next whole number. Now, let's look at what happens when you take p-hat times 1 minus p-hat. Some examples. Okay, if p-hat was 0.1, 1 minus p-hat would be 0.9. We multiply, we get 0.09. Now let's move p-hat up to 0.2, 1 minus p-hat, 0.8. We multiply, 0.16. Now we do it for 0.3, we get 0.21. 0.4, you get 0.24. 0.5, you get 0.25. 0.6, 0.4, 0.24. 0.7 be 0.21, 0.8 be 0.16. And we get 0.9. If you notice, p-hat minus 1 times 1 minus p-hat, it starts out at 0.9, goes up to 0.25, then goes back down to 0.09. So the largest value in this p-hat minus 1 times 1 minus p-hat is 0.25. That's the largest value you can get. Now, what if somebody tells you have a 50-50 chance? Is that a good thing or a bad thing? Well, 50-50 is the worst case scenario because it gives you the largest number here. This is 50%, 50%, 0.25. So 50-50 is your worst case scenario. So if somebody tells you 50-50, that's not good. All right, now, if no prior estimate is known, we're going to use what we just talked about, the worst case scenario, 0.25. So now we're going to replace p-hat times 1 minus p-hat with the worst case scenario, 0.25. So now N is 0.25 times the critical value divided by E quantity squared, and round up to the nearest whole number. So if you know a prior estimate, you're going to use p-hat times 1 minus p-hat. If you have no prior estimate, you're going to use 0.25, the worst case scenario. All right, so here's an example. A school administrator is concerned about the amount of credit card debt that college students have. She wishes to conduct a poll to estimate the percentage of full-time students who have credit card debt of $2,000 or more. What size sample should be obtained if she wishes the estimate to be within 2.5 percentage points with 95% confidence? If A pilot study indicates that the percentage is 34%. So in this case, there was a pilot study. So we need to gather the correct information from the problem. First, we need to know what p-hat is. Well, in this case, p-hat is 0.34. That's from a previous study. The margin of error, it's 2.5 percentage point, but 2.5 percentage points as a decimal is 0.025, and you have to put E in the formula as a decimal. And 95% tells you the critical value is 1.96 using the table at the bottom of table 5. Now the formula, N is p hat times 1 minus p hat times the critical value divided by E quantity squared. So I substitute values in. 0.34 times 1 minus 0.34 times 1.96 divided by 0.025. Square that quantity. If you can use your calculator, you will end up with this answer. And like I said before, we always round up, so your final answer should be 1,380. Okay, that's if there is no preliminary. I mean, that is if there was a preliminary of 34%. Now, part B, same problem, but this time no prior estimates are used. So we have no p hat, so E is still 0.025. 95% still gives us 1.96 for the critical value. The formula now is 0.25 times the critical value divided by E quantity squared. Substitute numbers in, 0.25 times 1.96 divided by 0.025 quantity squared. And this comes out to this number. If we round it up, we would get 1537. Now, if you think before, what did we have before? If I would go back, it was 18 something. So if there's no prior estimate, let me go back. It was 1380. Okay, 1380. That's less than what we just found. We found 1537. So 1380 was less than 1537. It didn't cut it down drastically, but it did cut it down some, especially if you had a long survey for these people to fill out. Okay, you're talking quite a few between 1380 and 1537. All right, now, some questions you should be able to answer from your readings. Okay, as the level of confidence increases, the length of the confidence interval. What happens to the confidence interval as your level of confidence increases? Now, I say look at this as throwing darts at a circle. Okay? Now, if you only needed to be 50% confident, that means if you threw 10 darts at the circle, you would need to get half of them in, 50% of them. So that's 5 out of 10 darts in a circle. Okay? What about if I said you needed to be 90% confident? That means you need to get 9 out of 10 darts in that circle. What do you think you want to do with the circle as the level of confidence goes up? Well, at 50%, you could probably keep your circle a little small. At 90%, you want to expand that circle. Okay? And that means that as the level of confidence increases, the length of the confidence interval will increase. Okay? Second, as the sample size increases, the length of the confidence interval will. Okay? So if we start off with a small sample size, we're going to get information. Now, what if we increase the size of the sample? Let's say we had 100 in our first sample. Okay? Let's say we have 100,000 in our second sample. Okay, what's going to be the difference between a sample size of 100, sample size of 100,000? Well, the difference is you're going to have a lot more data in 100,000, and it's going to be more accurate. So with a larger sample size, this means that we can cut down on the size of the confidence interval because we can be more confident. So in this case, it decreases. So those two things you should remember. And this brings us to the end of section 9.1.